Hi, this is the second lecture under the series of convolutional neural networks. So we have already discussed the basics of a convolution operation and how the convolution operation can be used to create transformations from between layers. Okay, and convolutional neural networks are help us to reduce the number of weights or number of theta values which are required for transformations between one layer to other, and significantly reduce the number of parameters which need to be trained, especially in problems where we have a lot of regional or temporal dependence in local regions or local time within the data. So there is a special relationship in the data where locality of the points around the locality of a particular pixel or a particular value play a major role in the perception of that point or that contribution of that point in the data. Okay, so you can go back to the previous lecture for more details. So in this lecture I will go above the I will build over the previous lecture in which I had already discussed the convolutional operation. So in this lecture I will look at how the convolutional after doing the convolution operation we can put a activation layer, because the convolution operation is essentially a linear operation. Okay, but what we want in neural networks is to find very complex nonlinear relationships. Okay, and nonlinear relationships between the input to the output. Okay, so for example here I have drawn one say a image, and this is one kernel. This is only a one dimensional image and a one dimensional sorry, this is only a two dimensional image and a two dimensional kernel. I have not included the channels. Okay, so there can also be multiple channels. For example, if this is the say red channel, we can have another green channel. So if this is a red channel, I can have a green channel and a blue channel. Okay, here I have say only shown one single channel of the image, or it is a single channel image. Then suppose this is a kernel. Then when this kernel moves over this image, you get a you can calculate every point on the output image. The output image will have a size which will be limited by the which will be determined by multiple aspects, such as the kernel size, the uh, the kernel the filter size. I will use the term kernel and filter many times alternatively. Both of these are similar. Okay, both of these are same. So suppose it depends, like the final output image size here will depend both on kernel size. The will depend on kernel size, will depend on zero padding, will depend on strides. Okay, so these all I have already discussed in the previous lecture. Now the output at this point of the output image will be simply a point by point multiplication of each kernel element with the corresponding image element. For example, here the output will be given by uh, here the output will be given by so x00 multiplied by theta 00, x00 multiplied by theta 00 plus x01 multiplied by theta 01 plus x02 multiplied by theta 02 dot dot dot. So every point here will get multiplied by every point here. So this multiplies by this multiplies by this gets multiplied by this gets multiplied by this. Okay, and then after that we do a summation of this. Okay, we do a summation of all these points, and whatever is the result, that result goes here. Okay, and after that so the kernel was initially placed from this point over this area, over this square. If the stride is say set to 1, then the kernel moves from this point to this point. Okay, so the kernel will now move to this point. then after that it will move to this point. Okay, so that way we can keep getting this point, this point, this point, this point, this point. We can calculate all these points. Now, but if we look at the overall calculation here, it's simply a linear operation. There is no nonlinearity about it. This is simply some multiplication, of element by element multiplication followed by summation. uh, Then after we do this, what we typically do is to add a bias element b1 to say the output of a particular filter. We add a bias, and then to this bias is added to every element. For example, plus b1 plus b1 plus b1 is done to every element. Okay, is done to every element in this matrix. After that, we apply a nonlinear activation function. Okay, so activation function is applied to this full function. This activation function can either be sigmoid, ReLU, leaky ReLU, or tanh. Okay, or there are some other activation functions which can also be applied. Okay, so this is for if you apply say one filter. Now we can have, so every filter will generate one output layer. Okay, no matter what is the size of the what is the depth of the image. Depth of image, and no matter how many channels are there in the image. Okay, you will always land up for every filter, you will have a single channel output. Okay, no matter how many channels the image has. So suppose this image has another channel here, and then another channel here. Okay, if the filter is of size 3, that means the filter is actually of size of 3 by 3 by 3. So we don't mention it, but actually the size of the filter is 3 by 3 by 3. If I say filter size is 3, that means it's a filter of the size 3 by 3 by 3, or 3 by 3 by whatever is the number of channels. Okay, whatever is the number of channels. So if this is number of channels here, C, then the filter size is always if I say the filter size is 3, then it is 3 by 3 by C. If I say the filter size is 4, then the filter size is 4 by 4 by C. Okay, so that when this filter moves over this image or this volume, so we do volumetric convolutions. Always remember, whenever you do convolutions, that in convolutional networks, it's always volumetric convolutions, where we multiply this. We take this full volume. Okay, and we multiply that full volume from this point to this point in one shot, multiply and add, and we get a single number which goes at one point, single point. Okay, then you move this by one stride, then you find the second number. So whatever is the number of channels. Okay, you will always get a single channel. Okay, single channel per filter. Okay, for every filter you get a single channel. What you can do is that you can apply multiple filters. You can apply, say this is the filter 2. Okay, for this you will get again another single channel. Okay, and you can apply filter 3, for which you will get another single channel. Okay, and then for each of these channels you can add a bias unit. Okay, and then a activation. Okay, for each of these units you can, so typically for a single layer, so you apply a activation. Okay, typically for a single layer you have all these activations. So this activation equal to this activation, and this is also the same activation. You don't apply different activations in a single layer. In the next layer you can have multiple different activations, but typically you only apply single activation for a single layer. Okay, that will become clear if it's not clear right now. But this is the way you do first you do a linear transformation here. This linear transformation then becomes nonlinear transformations after you apply activation function. After you apply activation function, you will still have the same. So after you apply activation function, let me see. So after you apply this activation function, you will still, for the first layer, you will get this 4 rows, 3 columns. Okay. For the second layer, you will get, from the second layer, you will get another second layer, and from the third layer you will get another layer. Okay, But all of these have now underwent linear transformations through the convolution and then non-linear transformation through the activation. Okay, but the final layer output is 4 by 3 by c, 4 by 3 by c here, which is the number of channels, which here actually is 3. So 4 by 3 by 3. But if the number of channels, so the number of channels here, say c out, number of channels in the output is not a function of number of channels in the input. Okay, number of channels in the input may be ci, but number of channels in the output is a function of co is equal to number of filters, number of filters. Okay, so here there are three filters, here there are three filters, right? One, two, three. If I increase the filters to say 10, suppose there are 10 such filters, then from a 3 channel image you can get a 10 channel image output. You can get an image output which has 10 channels. Okay, one behind another. Okay, so from a 3 channel image you can get 10 channel output. Okay, so depending on, so the filter, the number of channels in the output of a particular convolutional neural network depends on number of filters. Okay, and then activation can be chosen. So for now here, what are we training for? In cnnns we are training for these theta values. Okay, we determine that these are the these are the filters which we are looking for, and then we are training for. So there are how many theta values? For example, in this case, how many how many things we are training for in this layer? We are training for 27 elements, 27 theta values in the first filter, because there are three in this dimension, three in this dimension, three in this dimension. So there are 27 unknown theta values which we'll be training for in the training phase. Here then, here also there are 27, because there is also 3 by 3 by 3, and here also there is 27. So you have 27 into 3, 27 to 3 in this, plus 3. What are these 3? These are the 3 bias units, b1, b2, b3. So these also you need to train for. So for this layering arrangement, you have 27 into 3 plus 3 unknown, 27 into 3 into 3 unknowns. Okay, which you will be training for in this layering arrangement. Okay, then there is something which we call as the pooling layers. Okay, pooling layers help us to, pooling layers are have very simple operation. They have only, they have very simple task. Whenever we put a pooling layer, the task is to reduce the size of the output image. Okay, and not to do any other no activations or transformations. Okay, it's simply, simple task is to reduce the size of the output image from previous layer to the next layer. Okay, so there are two most frequently used operations, or two frequently used ways of two frequently used pooling layers. Okay, so there is average pooling or max pooling. Actually, max pooling is the more frequently used. Okay, and average pooling is less frequently used. In this, what we do is, if you say you have to specify what is your pooling layer size, what is your pool, what do you say, what is your max pool size, or what is your kernel size for a pooling layer. Kernel size for pooling layer. So in this case here, the kernel size is 2. That means we are pooling by using a 2 by 2 kernel. 2 by 2 kernel. So we move that 2 by 2 kernel over the image. If it is a max pooling, we look at what is the max in this 2 by 2 kernel. This is the max. Okay, this 13 is the max. So that 13 goes here. Okay, that 13 goes here. Similarly, after that you move, and then also you provide what is the stride. You also need to tell what is the stride. What is the stride. Here the stride is 2. That means the pooling layer will shift directly from this point to this point. Okay, the stride is 2, so the next one will be 23. But if the stride would have been 1, then the output would be what? Output would have 3 elements on each side. Okay, so the next jump would have been from this point to this point. In case the output would become, the first one was 13, the next one will become 17, and next one will become 23. Okay, so if the stride was 1, but here the stride is 2, here the stride is 1. Similarly, the average pooling, you can very easily guess, it is the average. Average pooling is the average average within the pooling region. Okay, so again you can provide um, what is the kernel size of the pooling layer, and what is the stride, okay. If you provide this, then if you have any image, for example, if you have an image of 100 by 100 and you put a pooling layer, max pool layer, okay, with a kernel size of f equal to 2, which is the kernel size or the filter size of 2, and stride equal to 1, then immediately the size will become 50 by 50. Okay, and this max pooling is applied layer by layer. So suppose, so the number of channels do not increase or reduce by applying max pooling. So if you have a particular layer under which you have, say, 100, this is 100 by 100 by, say, 50 channels on this side. So after applying say 100 by 100 by 25 channels, so there are 25 channels on this side. Then after applying max pooling, you will have 50 by 50, 50 by 50, but the number of channels, every channel will reduce. Every channel, the max pooling layers will be applied to every channel, and you will have 50 by 50 by 25. So you will still have 25 channels remaining, but the overall dimensions of the number of channels will remain preserved, but the width and the height, both of them will reduce. Okay, so this is the idea of pooling layers. Now, how do we really construct a full neural network using the above ideas? So let's take a classic CNN architecture, which is a LeNet 5. Okay, a classic CNN architecture. Okay, LeNet 5. LeNet 5. Okay, the paper for it is available on net. I will also share it under this where in the Google Classroom, where I will share this video. In the same place I will share that paper. It's a very simple to read paper. You can go through it and you will be able to see that whatever you have learned till now in neural networks and CNNs will start, you will be able to understand the paper by looking at, by reading through it. And um, and I strongly recommend that you go through that paper. Okay, so in this they have targeted to solve a single channel to image recognition problem. So suppose the initial image which you want to recognize is of 32 by 32, and number of channels is 1. Okay, so this is a 32. So this is a 32 by 32 by 1 image. Okay, after that you first apply a convolutional layer of filter size equal to 5, and strides equal to 1, and number of filters, which is filter count is equal to 6. Okay, filter count equal to 6. I will also write it as f underscore n. Let me write it as f underscore n is equal to 6. So there are 5 by 5 filters. So these will be 5 by 5 filters. Because the depth here is only 1, so the filters will be like this. Filters will be 5 by 5 by 1, which will be applied, but there are 6 such filters. there are 6 such filters. So for every filter, you will have an output image. Okay. So when we apply this filter, you will get a by applying the first filter, you'll get 28 by 28 image. Okay, because you can apply which formula, the formula which I discussed in the previous lecture, to find out that the width of the output image and the height of the output image. Here the padding, there is no padding, so padding is 0. Okay, so we are not padding anything around the image. We are not padding. There is no zero padding. So when you um, so this is a 32 by 32 by 1 image. We convolve it with a 5 by 5 filter. Okay, then you get a 28 by 28 image output. But there are total 6 such filters which are applied one after another. So for every filter, you get a new channel. Okay, so you get a volume. So the output which you get is a volume. The volume is like this. So the volume has a size of 28 by 28 by 6. Okay, so let's make it let's smaller. So it is a 28 by 28 by 6 volume after you apply the first layer of convolution. After that, we apply a average pooling layer, which is nowadays rare. We typically use max pool in most cases. But this was one of the very early architectures in which they applied average pool. F equal to, now say we after, so for average pool, our filter size is 2. That is, the pooling layer sizes, pooling kernel size is 2 by 2, and strides equal to 2. Okay, so f equal to 2 and strides equal to 2. Okay, so this means just like the way, just this pathway, you first apply to this, then you jump by 2 and you apply to this, then you jump by 2 and apply to this, then you jump by 2 and apply to this, and take the average of each kernel. And then, so what will happen is, if you do this, the kernel size, the overall image size for every layer in this volume would reduce to 14 by 14, but the number of channels will be saved. Number of channels will not change, they will remain 6. So it will become a 14 by 14 by 6. Okay, after that we can apply we apply a convolutional layer. Okay, which is if filter size, just a minute, let's see if I can. So after this, we apply a convolutional layer with a filter size f is equal to 5, and f underscore n, which is number of filters, equal to 16, strides equal to 1, and padding equal to 0. So when we do this, you get what? If you apply this formula, you will see it comes up. Apply the previous formula which we discussed in last class. You will find the size of this image will become 10 by 10, and number of channels will now become equal to number of filters, which is 16. For every filter, you get one channel more. So when I say 5 here, when I say filter size equal to 5, that means the filter size is 5 by 5 by 6. Okay, because the filter size, when I say 5, that automatically implies that the number of channels in that filter is equal to the number of channels in the previous layer. Okay, then only when this volume convolves with this volume, you will get a single channel output. Okay, when this volume convolves with that volume, you will get a single channel output. Okay, and so then when we apply 16 such filters, you have 16 channels output. Okay, so then the output volume is now 10 by 10 by 16. After that, we apply average pooling again. Okay, so you can notice one important feature in this, or one important overall feature in this architecture, is that we first do a convolutional layer, then we do a pooling layer, then a convolutional layer, and then a pooling layer. So convolutional layers and pooling layers are typically in most CNN architectures follow alternatively. So every layer tries to reduce the number of amount of information along the x and y dimension and increase the number of channels. Okay, so every layer is trying to reduce the dimensionality in the x and y dimensions and is trying to increase the number of channels in the y dimension. Okay, um, so if you do average pooling, okay, with f equal to 2 and stride equal to 2, again, so now this will become 5 by 5 number of channels are preserved in the average pooling, in any kind of pooling actually. So number of channels will become 16. So 5 by 5 by 16. After that, now initially what was the amount of information which was there in the image? It was 32 by 32. Okay, 32 by 32, which comes out to be uh, just a minute. So we had 32 multiplied by 32, which is 1024. So we had 1024 pixels in the initial image. If I would have flattened it, my input layer would have 1024 inputs. Now what happens is, after going through this loop, along after going through this process here, I have this volume. Okay, I have this volume left. This volume, I then go, I do a flattening. Okay, I flatten this layer. Maybe I'll draw it like this. Okay, I flatten this layer. So what happens is, after flattening, I get all these as inputs. So I flatten this layer. So how many inputs I'll get? I'll get number of inputs I'll get is 5 into 5 into 16. Okay, so let's see what's 5 into 5 into 16. Okay, which is 400. Okay, so initially you could see that if I would have went with this method, with the direct flattening and then followed by fully connected layers, which is the standard neural network architecture, we would have got initial input itself 1024 inputs, and after that, each layer would have their own hidden layers would have their own neurons, and the overall number of parameters which we needed to train would have been larger. But here you can see, after going through this, I have, after flattening, I have how many? I have 400 here. Okay, 400 inputs, which is then fully connected. Then we have a fully connected layer. Fully connected layer means every neuron is connected to every other layer, which is the standard architecture of a neural network, uh, which you have studied before the convolutional networks. Okay, so then it goes to a 120 neurons fully connected network, from which it goes to 84 neurons, from which it goes to a soft max layer. I'll come back. I'll talk about soft max. Um, I'll talk about softmax classifier in the following lecture. But overall, this is the architecture which it follows. And softmax. So don't worry about this right now. I will talk about it in the next lecture. Okay. Or should I? I'll talk about softmax layer. Okay, in the next lecture. But overall, this is the architecture. Let me see if I can zoom out a little bit, zoom in a little bit. So yeah, so this is the classic CNN, classic LeanET 5 architecture for handwriting recognition. So total number of parameters which are there in this to be trained are 60,000. Okay, 60k, and approximately 16k, and it's used for recognizing handwritten digits, and it uses sigmoid activation functions in between the CNN layers. Okay, in between this convolution layers, it uses sigmoid activations. Okay, so there is something called as softmax I can talk about, but let's talk about in the next lecture. I will attach the um, I will attach the paper with this video and you can go through that. But just to, we can also have, like, if you are not aware of softmax at this stage and you just want to have a single output, you can also put a single output neuron. Okay, number, just a single output neuron, depending on, or you can put 10 neurons if you are say recognizing handwritings. You can put 10 neurons and each one is responsible for a single handwritten element. If you are recognizing 0, 1, 2, 3, something like that. Okay, so this is the architecture which can be used. Okay, so that's it for now. I'll come back again maybe with one more lecture dealing with some other aspects of some other aspects of CNNs and also some other architectures of CNN. I will do one demo of coding of how to apply CNNs to large data sets of images to do image or object recognitions. That will be very interesting and it will really make you feel very empowered on many things which you can do with CNN. So hope to see you soon. Thank you.